Today, we are diving into the invisible force that makes digital world spin. This is rotational motion, the MCG spin engine, where physics meets pixel to power everything from game characters to robotic arms. Okay, let's start with the fundamentals. Every spin begins with three key concepts: the axis of rotation, angular displacement, and angular speed. Okay, let's move on to the next slide. Okay, in here, we can see angular displacement and angular speed and the formula. Here's the math behind the motion. Angular displacement tells us how far one full rotation equals 2 pi radians or 360 degrees. The angular speed, which the W shape, is simply theta divided by time. Okay. This formula, it's the engine under the hood of every smooth spin in 3D graphic, from camera sweeps to character turns. Okay, let's see the formula in action. Okay, so in our virtual centrifuge here, we simulate 12,000 RPM, the spinning one. And in manufacturing, we gave an example of precise angular control that guides robotic arms with millimeter accuracy. As you can see these both, here are the examples. And yes, every frame, this simple equation runs the theta equal by angular speed times time. Real-time, real-world simulation. Whether it's game engines, camera control, or scientific visualization, math doesn't just animate, it simulates reality. Okay, moving on to the next section. Okay, imagine a ceiling fan blade completing a full rotation in 2 seconds. What's its angular speed? So, here's the information already given. We apply the formula on here. We type the speed of the fan and the time given. We calculate it and we get this 177 radians. In every other game engines, this same calculation controls propellers, wheels, and rotating object, making 3D scenes feel alive. Okay, so from physics to pixels, rotational motion is more than theory. It's the engine powering digital worlds. Thank you.
Thermodynamics is the study of energy transformation between work, temperature, internal energy, and heat. There are a few key thermodynamic concepts that are important to note, which are heat, temperature, internal energy, and Gibbs free energy. The 3 laws of thermodynamics are fundamental in understanding thermodynamics. The 0th law states that when 2 systems are in equilibrium with a third, they are all in equilibrium with each other. The 1st law states that energy cannot be created or destroyed, only transformed from one form to another. The 2nd law states that in any spontaneous process, entropy of the universe will increase. Now let's correlate how thermodynamics is applied in real-life applications in biotechnology. First of all, bioreactor control. The 1st law focuses on conservation of energy where energy is balanced between heat generation and cooling system, and this is vital for bioreactor to ensure cell growth at optimal temperature. Next, enzyme reaction. Enzyme manipulates activation energy, a component of Gibbs free energy, to speed up its reaction without changing the overall spontaneity or equilibrium. As such, we are able to increase specific enzymatic reaction. Next is polymerase chain reaction thermocycling. PCR thermocycling requires specific heat control to ensure DNA is amplificated. Similar to bioreactor control, the 1st law focuses on conservation of energy where energy is balanced between heat generation and cooling system. Last of all, cryopreservation. Cryopreservation is cooling biological material to very low temperatures. A cooling system is needed to ensure controlled cooling rates to avoid damaging the cells. Energy in thermal processes. Thermal energy is the total kinetic energy and potential energy of particles in a substance transferred as heat. Heat is the energy transferred between objects due to temperature difference, where temperature is the average kinetic energy of particles. So high energy will flow to lower energy until it reaches equilibrium. There are 3 methods of heat transfer or thermal energy transfer, which are conduction, convection, and radiation. Conduction is heat transfer by direct contact between particles. Convection is the heat transfer by fluid movement of liquid and gas, while radiation is heat transfer by electromagnetic waves. Now let's talk about real-life application. The simplest example is cooking, where heat is conducted throughout a frying pan when frying. But let's talk about examples applied in biotechnology. First of all, polymerase chain reaction or PCR. This is the application of DNA where precise thermal cycling is done using a conduction of a metal block in the PCR machine. Next, sterilization. In biotechnology, sterilization is done by a machine called autoclave that uses convection to carry hot steam to eliminate microbes. Last of all, fermentation. Fermentation requires a suitable temperature environment to occur efficiently. By utilizing the methods of energy transfer, which is conduction, convection, and radiation, we are able to achieve optimal growth and yield. These applications in biotechnology will contribute in medicine, research, and also daily life such as food manufacturing.